Salve, and welcome to Lecture 8 of the Introduction to C# course. Today we're going to talk about errors and exceptions. In an ideal world, all of our inputs from users would be exactly what we expect, all API calls would always succeed, and there would be no need for managing any sort of errors. Unfortunately, we do live in the real world, and in the real world, errors happen all the time, and a lot of the quality of software has to do with its ability to correctly identify, manage, and recover from errors and exceptions. In this chapter, we're going to talk about exceptions and how this built-in C# mechanism allows us to sort of build a parallel path of computation that manages errors. I will also show an emerging pattern, because exceptions are a bit, I don't want to say it's a legacy, but it's an old school pattern that is still used almost everywhere, but we will also see an emerging pattern of error management, which has to do with returning containers that force the user through polymorphism and inheritance to unpack a piece of data to check whether or not we have a result or an error. This is going to be a much lighter lesson than the previous one, a lot shorter than lesson 7, so let's enjoy it and good luck. Alright, now let's say that we have a divide function. Divide takes as input a and b and returns a divided by b. Okay, so nothing particularly exciting, but if b is equal to 0, then we don't really, obviously you're not going to write a method like this, but you can imagine you've been passed an empty collection and you need to calculate the total, then you need to find a particular element in an empty collection, or there are no articles in the database, and you need to, find the most recent article, etc. So it's very easy to imagine that there's a lot of validation that needs to happen. We're going to use a bit of a silly example indeed. If b is equal to 0, then, well, it doesn't make any sense to divide a from b, to divide, to perform the division, because, dividing by 0 breaks the laws of mathematics and will result in an error. So in this case, when we identify an invalid parameter, we can throw an exception. Now, in this case, C# is suggesting an arithmetic exception, but for now, we will just throw a very normal exception. Argument to an exception is usually a string. We can also nest exceptions, so we can, if we already had an exception and we want to sort of decorate it with more information, then we can actually wrap a previous exception into another one, but the message is very important, and the message could be error. The b parameter to the divide function cannot be 0 when performing, and then let's say a divided by b. Okay, then we're providing a little bit more information. I think the IntelliSense has frozen. Alright. Now, when we call divide, so let's say that here in console.writeLine, we just want to call divide and pass it 10 and 0, and we try to run this program. What now happens is that the program actually stops running at line 11. There are languages where, so the TypeScript, for example, is a language that tries to hobble on, and so tries to actually return undefined or not a number in many cases, where C# would actually throw an exception, but C# throws exceptions much more often. And when C# throws an exception and we don't catch this exception, then the program is stopped. Like literally, the program gets interrupted. No more instructions are done. So the instruction I have on run 12 is never executed. But this is not an option that we always have. So in order to catch exceptions, we have the try catch block. So imagine that we have an operation and we know that this operation might return an exception. Then we catch, and the argument to catch, so in between the try curly brackets in the block of try, we attempt division. But if the exception is thrown, then in the block of catch we declare the variable that will be bound to the exception thrown by the code between lines 11 and 13. And here we actually get the code that can be executed as a response to the exception. So I could say console.writeLine error and then e.message division not successful. But then we can continue with line 19. And now you will see that, well, first of all, so here we got a message that says unhandled exception. So this is the behavior that the C# runtime automatically adds. So it just says, well, there was an unhandled exception, so this caused the program to crash and stop, and it shows the message that we sent, plus the place, the stack trace where the exception was generated. But in this case, and I'm removing this extra throw statement, we just print that, okay, division was not successful. And here we could have some retry code, we could ask the user for more input, log a message, etc. So here we have to decide how is the program going to cope with this error. And well, this is actually a very good practice. And now you see that, well, we don't have this gigantic error. We just see, oh, okay, maybe there are too many error words. Okay, we just see error. The b parameter to the divide function cannot be 0 when performing 10 divided by 0. Division not successful. Yeah, okay. Now it doesn't look that pretty, unfortunately, the dot and comma, but let's leave it be. Notice that here C# automatically puts a throw statement. We'll look into that in a moment. Okay. Something that is also very useful and that we might want to incorporate in an exception, because suppose that you get to see a message like this. The problem is that clearly the error is not divide itself, but the context in which divide was being invoked. So, for example, if b comes from the number of items in the shopping cart, then we don't really care about the fact that the error happened in divide. The error actually happened in the context in which divide was called. So you see this whole thing here with program.cs line 6, which would happen to be here, and also program.cs line 11, which happened to be here. Well, this is the stack trace, and it is actually possible to visualize the stack trace, or to access the stack trace and to include elements of the stack trace in the exception message whenever needed. So system diagnostics, stack trace. Now, what we can do is we can create a new instance of the stack trace. And actually, we can even say that we want file information, like which files and line numbers did we get calls at. And well, let's just look at this. And here, when we're running the when we hit the exception, let's take a look at T. Look at this beauty. There are 2 frames, and well, you can actually see that. Yeah, let's see what else we have here. We don't get IntelliSense, but well, it's basically a sort of array indeed, with a bunch of frames. We have only 2 because one is for divide and one is for the main program. And if you look at toString, it's actually showing the message that we have, but we can actually process this. Let me see. Yes, we can say get frame of 0. Yeah, this should be done. This should be done better, obviously, and in a parameterized way. And by the way, calling this stack trace thing, this creating an instance of the stack trace, is really slow. But if we're dealing with exceptions, probably, well, some slowness is acceptable. And there's the trade-off, of how often does the exception happen, and how difficult will it be to, if it's an actual error that you really don't want to happen with some serious consequences, then it's absolutely worth it to invest a bunch of CPU cycles that slow down the program, but make it possible to actually diagnose what the heck is happening. Now let's take a look at F1. And well, you can see that F1 contains the information, oh, so cool. Offset 150 in file, line, column, and then you can see, the whole path of the file, the line, which was line 7, and the column. So cool, this. Yes, and then if you get a frame 0, that's the frame of the divide function. But if you get the parent frame, for example, because you suspect that the problem comes from the parent frame, because the problem seems to come from the caller, then here okay, this is the instance of divide that was called by the main function at line 16. But if you're calling divide from 50 different places in your code, as is often the case for some inner logic, yeah, the logic happens, the error happens in the inner logic, but the point is, who called this with the wrong parameters? And with these frames, you actually get to that extra little context. Now, remember that originally the IntelliSense suggested that we would throw an arithmetic exception, which would actually happen to be good advice. But what if we want to be even more specific? Well, we can define our own exceptions. So, for example, I could say that we can have my divide by 0, division by 0 exception, which inherits exception. Anything that inherits exception may be thrown just like any other exception. So, for example, we could say we have the numerator and the denominator. Oh, deviation, no, denominator. There we go. So we actually want to carry all the information about this error. And now let's generate a constructor. The exception itself, well, it has a constructor without parameters, but this is not enough. We also want the message, and I'm also going to say that we call base with the message. Yes, too many curly brackets. Very good. And then I'm going to override the virtual message property to say Okay, so base.message when dividing, and then numerator divided by denominator. Yes. So by doing this, I'm basically encapsulating an underlying message within the, let's say, framework of the exception. And I'm also adding a, let's say, obligatory bit of the message being the context of the error, if you want. Now, I can throw my division by zero exception, which requires A, B, and well, what message? For the message, actually. Let me think. For the message, let's actually use the stack trace. T is equal new stack trace. Yes. Okay. Var error context, and this will be an empty string. I'm going to assemble it a little bit better. For I from 0, now we're going to go through the stack frames. I smaller than t dot frame count. And I do want the file information, by the way. And then the frame is going to be trace dot get frame of I, of course. And let's see what the frame gives us. File name and file line number. Okay, I would say this is enough. So what we do is we say error context will be will get frame dot get file name colon frame dot get file line number, and let's just say a semicolon, you know, let's not make this more complicated than it needs to be. So now we have the my division by zero exception. We get we add the information that is we get the information that is required by the my division by zero exception, which is A and B, and in this case we also want to add a custom message which just contains the error context from the stack frame. And why are we complaining here? Yes, of course, because it may be null. It's okay, we can ignore this. It's not going to be null because I is always going to be within the boundaries of 0 and frame count. So we are going to be safe. We should be careful because, well, this might accidentally throw a null reference exception, which is a very common exception, by virtue of trying to do something wrong with the error handling itself. So it can actually happen that you think you're managing your errors, but actually your error management code is introducing new errors that throw exceptions that you're then not catching because, well, all right. So and now you see error, and then you can see the file and line. It's very nice. And then you see when dividing 10 divided by 0, and then division not successful, which is the message that came out of the try catch block. Now, in this case, we're catching an exception, but actually the catch block can be even more nuanced than this. So we can say my division by zero exception, and we're only going to catch exceptions that are either my division by zero exception or that, oh, there's a typo. The typo is gone. Or an exception that inherits my division by zero exception. But suppose now that our our divide method actually gets as input, let's say, an array of strings. And declares b as strings dot length. Okay. Oh, the number of things that can go wrong with this. For example, well, okay, so if the array is empty, this is going to work. But an array may be null. And, well, very nice, we're getting the warning, okay, excellent. So we are sort of, well, okay, let's complete this discussion. Let's complete this discussion, but then, yeah, indeed, this is an important suggestion that we're getting. Because we're getting a complaint that says, well, it could be null, you know, because, look, here, and this is just because C# is still a bit mild, but just like TypeScript, these warnings will become compiler errors eventually. But here it's saying, okay, you're passing null, but here you're declaring strings to be an array that doesn't allow for null. And if we say, no, but this may be null, then the warning is moved here saying, yeah, you should have checked this for being null. Very good. Now this can throw a null reference exception, but let's say that indeed we are forced to check. And we say if strings is, if strings is null, then here we just throw a new argument null exception. Oh, name of strings, very good. Okay, so this just puts the null parameter. Now, let's go back to having an empty array of strings. Let's run this. And, well, we get the correct catching of our exception. But what if we attempt passing a null to divide? Now we get an unhandled exception despite having a try-catch block. Why? Because my division by zero exception has nothing to do with argument null exception. So you could say, okay, this is what you do if my division by zero exception has been triggered. We can also catch specifically an argument null exception. And in this case, we can say that, well, a null argument was not expected by divide, and divide couldn't continue. And now, all of a sudden, we see error value cannot be null, parameter strings, and the null argument not expected while doing division. And here again we might decide, okay, if this happens often enough, the problem is obviously not inside divide, so getting the context in the form of the stack trace is always potentially a good idea. And then if we want to say that we have a sort of, well, catch anything else, then here, well, we don't know what went wrong, but at least we can show it. Something unexpected went wrong, because when you get an exception is like the most unspecific sort of exception, and when you get it, it means really that there is no better kind of error that we could talk about. In this case, the exception handling code that we have in the various catch statements is in the main, so there's no further context. Usually, when you catch an exception, you catch it in a place where, well, you can't continue processing. So you have a function, and this function really needed a result to continue processing, but yeah, it cannot. So it has to catch the exception and figure out a way to cope with it. Sometimes, though, the place where you catch the exception has to re-throw the exception to its parent or to its caller. For this we have the throw statement. In this specific example, I'm going to run this, but it doesn't make a lot of sense because now I have an unhandled exception. So that's really not good. But the idea of throw is that, okay, I catch the exception here, I do something, and doing something might also be performing some cleanup or sending an error message to an API call to another server, whatever. But then, yeah, you're like, also, this context has to fail. And you can say, well, it fails in exactly the same way as the exception that we got. So this throw, I think they could have also called it rethrow, to be honest. Just rethrows the last exception you catched. So this is also useful to know when you find code like this. But also, another very important statement when dealing with exceptions is finally. Finally runs code whether or not we got to the end of the try block without errors, or we caught an exception here, finally, will always be executed. So let's say that we have this bit is executed anyway. Let's say we have a bit of logic that must run no matter what. Let's rerun this. We get the value cannot be null, but we also get the this bit is executed anyway message. And let's have an array with 2 strings. So this is just going to work. And you see this bit is executed anyway. Finally, it's very useful because let's say that you open sometimes you create resources and these resources need some cleanup. Maybe you opened a database connection and you have to release it, or you have maybe a pool construction of connections and you have to return the database connection to the pool, etc. So sometimes you want to be able to do these things, and finally is a way to control the fact that, okay, even though an error occurred, we have some cleanup code that needs to happen anyway. A pattern that is alternative to exceptions is the pattern where we actually encode the possible errors in the type, especially in the return type of a function. And, well, why would you want to do this? I almost hear you asking. So let's say that we have a null here. Well, why would you want to do this? Because right now, look, I've removed the whole try catch, and the language doesn't complain. Why doesn't it complain? Well, because there is no rule that says that you cannot run code that will throw an exception, and that you have to manage that exception. And it means that exceptions can actually go pretty much unobserved, because let's say that this function was written by another team member participating in the same software development project as you are. And, well, maybe there is a comment or documentation stating that divide might throw an exception, but in general, if you're importing this from another project, you don't want to look at all the source code that you're importing and using. You just want to use it without thinking about it. And the problem is that the only thing you really have access to is the type definition. And if the type definition doesn't say anything about the exceptions that are thrown, and this is historically more or less now not super successful experiment that Java ran by having the exceptions part of the signature of a method and forcing you to actually catch everything. But yeah, because the signature is everything you have and the exceptions are not part of the signature, yeah, there's a big blind spot here. So sometimes you might want to say that we define, for example, an interface. I division result. And I agree, this is not necessarily the easiest pattern, but then we can have a record, success, with just a value, and this is an I division result. And then we have a null argument, and this is also an I division result. And then we have divisor is 0. Oh, pardon, and let's actually call this error. There we go, yes. And, well, let's say that this is enough. Now, let's say that our divide method, or our divide function, pardon, returns an I division result. Okay, now here we don't just return A divided by B, but we return success of A divided by B. And here, instead of throwing, we return a new divisor is 0 error. Well, and we want to have a message anyway, so let's say that now, let's do this properly. Int numerator, int divisor, and string message. Okay. And why is it unhappy now? Oh, of course, new. Yes. And also, of course, here we're not going to throw new argument null exception, but we're going to return a new null argument error, which of course needs a string message. Okay. A side effect of this, and this is not a minor side effect, is that, well, right now we can just call divide safely, and now, well, right now we get a null argument error. But what if we really want to know what is happening? Well, now we can simply switch on divide, and we can say, okay, you know what? Well, and well, there could also be other kinds of errors. Yeah, forgive me. I'm actually going to add a generic error, and I'm going to make this even stronger. So try blah blah blah, and at the end, when we catch an exception E, what we do is we say return new generic error with e.message. There we go. Okay, so now if we get a success S, then we can simply return s.value. Otherwise, if we got a null argument error E, then here we can simply, well, you know what? I'm just going to be lazy and just going to put e.toString, and for all other cases, yeah, I'm not going to care that much. You get the gist of it, I hope. Then here I'm also going to put yeah, okay. I'm going to be very lazy now, but here what we're doing is basically we get a result, and if we want to unpack the result, yeah, we're forced to use a switch statement, and the switch statement kind of encourages to also indeed provide the, well, encourages, forces us in a sense to manage the fact that, yeah, if we want to see that we got a success and we don't check the rest, yeah, we get a warning, and eventually this will become a compiler error because C# is getting stricter and stricter by the release. And yeah, at least the fallback case that says you have to deal with errors, but also you can have the other cases like you can catch for null argument error, you can catch for divisor is 0 error, etc. Now, this adds a layer of type safety. Yeah, now for the null argument error, I'm just printing the error message itself. But this level of type safety can greatly increase the readability of your code, makes type definitions like this one a lot more useful, because all of a sudden divide gives you an I division result, and if you check the I division result and you're like, okay, where is it? Then you can see, okay, oh, it's used here, and yeah, it's so it's either a success, null argument error, divisor is 0 error, or even generic error. And yeah, so this type signature went from not saying anything at all, just saying, okay, the division returns an int, yeah, and it looks like it always returns an int. No, it doesn't always return an int. It returns a type that is actually properly descriptive. This is a pattern that has been very used in functional programming, and it's an extension of the option data type, which has now actually come to Java in recent times. And after so many years, it's actually almost funny to see that indeed this pattern has been recognized as so much cleaner and easier than just abusing exceptions everywhere. So yeah, I would say whenever something can fail with a relatively high probability, changing the return type is a much saner option because it forces the users of your code to deal with this exception, to deal with these exceptional situations, even if you're not returning an exception or throwing an exception, because by returning a value that needs to be unpacked and switched on, yeah, you are forcing whoever is using your code to deal with the fact that some unpacking needs to happen, and the unpacking forces also the structural check of, okay, but do I actually have a value or something else? So this is for things that happen, unexpected situations or unavailable results that present themselves quite often. When you have an error which is very uncommon, then exceptions still make sense, because you might want to not really deal with exceptions in your inner logic, but just deal with exceptions like at a higher level in the program, like closer to the main and further away from the little functions. So yeah, for example, let's say that you're trying to compute a message about a shopping cart or some statistics, and for some reason the user tried to access an area that they shouldn't have accessed with an empty shopping cart. And you have to produce the message or the statistics. Okay, then this might happen relatively often. So you're going to just produce a fallback scenario or a fallback message. And in that case, this pattern we have just seen of returning complex data types, encoding success or the kind of error, this is super useful because it will happen so often that you want to include this kind of error in your happy flow of the program. If you have things that are rare and outside of your control, like trying to open a file, but yeah, something doesn't work at the operating system level, that it's okay to treat this as an exception and to just manage it in a bit of a generic way at the top of the program. So it's okay if the program sort of fails because, yeah, something catastrophic happened. Then you don't need to try to return all of these little errors because, yeah, if it's catastrophic and outside of your control, just find a way to fail graciously at the top level, and that's it. This brings us to the end of this actually short and hopefully reasonably sweet lesson. I hope, of course, that your programs barely have to deal with these exceptions because the happy flow is all that is going to happen to your applications. But if that's not the case, I hope this was useful, that you enjoyed it a little bit. As always, thank you very much for being here. And until next time, bye-bye.